So back in chapter 4, we looked at some causes of cell degradation qualitatively, and now in this chapter we have seen a quantitative approach to two of the more significant degradation mechanisms. So going back to chapter 4, you'll remember that there was quite a list of possible degradation mechanisms that are known about. And only two of them have models that we've presented here. So much work remains to be done in this area. And this is very clear. If we're going to use physics-based models of degradation as a basis for controls, we need to get more models. So the first activity needs to be done by material scientists and electrochemists who are good at modeling phenomena that they see. As controls engineers, it's, in my opinion, not really our job to be looking to make the first principles partial differential equation models of degradation, because I expect there's a lot that we don't know about how chemistry works and so forth. So it's best to let the experts work on those. So I'm hopeful that we'll see over time more and more models of degradation coming out of research groups studying degradation of lithium-ion batteries. But then, once we have partial differential equation models that are validated and verified against real behaviors, then the controls engineers can come along and propose reduced order models and validate these models against the PDE models. And if the PDE models have already been validated against the truth, then that's a valid approach. So if we make reduced order models suitable for implementation in controls, then we can design controls, and we can define different ways of computing power limits to slow aging. And that's a question. How do we do that? How do we use these models to compute power limits to slow aging? And in the rest of this chapter, we'll give some ideas. These ideas have not been exhaustively validated in any sense, but these are ideas that we hope will become very valuable ways of computing power limits in the future. And the key point is this. We've looked at only two mechanisms, but in those mechanisms causing SEI growth, causing lithium deposition, nowhere in those models did we even see a term describing cell terminal voltage. That isn't the cause of degradation. So it's possible that when cell terminal voltage is too high or too low, that indirectly implies that cell degradation is happening because you're inferring something about the internal states of the battery cell, but nowhere in those equations did we see cell terminal voltage. Instead, there's some kind of an internal stress factor, and in both of the mechanisms that we looked at, it was phi s minus phi e. And we have a transfer function for phi s minus phi e, and that was back in the previous course. But we can compute this if we have the cell parameters. So if we can compute phi s minus phi e, then we can also compute the degradation that we expect will happen due to proposed different profiles of future current versus future time. That's the whole idea here. If we can make models that are coupled directly to whatever internal stress factors exist, in this case phi s minus e, and if we can model those internal stress factors, then we have a hope of implementing better controls. And that's what I think I say here. So if we assume that the degradation mechanisms can be modeled, it makes more sense to compute power limits based on predicted capacity loss or predicted impedance rise due to some future current versus time or future power versus time than it does to compute the power limits based on the voltage limits as is done right now. So there's a lot of work to do. There's probably years of work to do before this is practical. I think that in the short term we can probably show that a proof of concept, a feasibility study, and that's what we're hoping to do with one of our research projects that's ongoing right now. But for this to be a comprehensive solution, there's a lot of work to do in this area, but that's okay. I think that the benefits are worth it. In the next couple sections of notes, the remainder of this course, we're going to introduce very briefly some optimization methods that might be used to compute physics-based power limits based on degradation mechanisms. And this topic we're talking about right now is extremely short, and it's just an introduction to the introduction, if you will. First, there's at least two controls problems that we might want to consider. There might be a third, as mentioned in the footnote, but the third one is not something that we're thinking about right now in our research team. But in a plug-in type vehicle, the extended range electric vehicle, the plug-in hybrid vehicle, or the pure electric vehicle, at a regular interval, the battery pack is charged from an external source, from the AC mains. When we're charging the battery pack, we have a lot of flexibility as to how we do it. Do we want to optimize speed? Do we want to optimize something else? So we can come up with different ideas of what is optimum first, and in the sense that we're thinking about here, we're optimizing some criteria subject to also at the same time minimizing degradation that happens. And the two mechanisms that we looked at, the SEI growth and the lithium plating, are worst when we're charging. If I'm not charging, lithium plating can't happen. And if I'm not charging, the SEI layer growth is going to be extremely slow, just kind of resting. But if I'm charging, both of those are going to be accelerated. And so how do I consider that in my charging strategy? Do I want to charge really slowly, or do I want to charge quickly? How should I charge it? So we're going to look at that starting in the next section. And fast charging is kind of a big idea. We already talked about, I think back in chapter 2, maybe it was chapter 1, that when we're charging an electric vehicle using household AC, the fastest we're likely to get in the near future is 6.6 kilowatts, a level 2 charge. And at that rate, it would take hours to charge a battery pack, even at a relatively slow rate. But the fast charge we're thinking about here is, let's ignore that. Let's suppose that future houses have higher service capabilities, or we have something similar to a present-day gas station where we can drive in and try to charge our battery pack in a few minutes. Is that possible? Is it feasible? And if it were feasible, what would be the optimum profile of power or current versus time? And we can make quite a bit of progress to determining what that looks like, and we'll see that in the next sections. For any kind of electrified vehicle, including a hybrid, while the car is being driven, we can also ask these questions. What is the maximum charge power that can be sustained over the next delta t seconds, and what is the maximum discharge power that can be sustained over the next delta t seconds, while minimizing degradation in some sense? So this is just like the power limits calculation we did back in chapter 6, except our criteria is no longer using voltage limits on a cell, kind of arbitrary voltage limits, but we're now looking at some kind of internal electrochemical limits that we'll be employing instead. So these two different problems have different answers to them. They're really quite different in how they are stated and in how they could be solved. So we'll look at the ideas that we're thinking about in the next few sections for how we might solve these problems.